What is up, everybody? We are on to our last section or last lesson for transformation. Okay, now this has nothing to do with any of the rules, so we're not going to do any translation, rotation, reflection, or dilation. This is just simply focusing on symmetry. So it's a little bit different than the other ones. It's more kind of just understanding what symmetry is. So there's not going to be any numerical formulas per se. Actually, there is one, but it's not going to be any graphing or anything like that. Okay. So here we go. So when you think of symmetry, right? When you hear people say like that figure has symmetry, right? What do you think of? Hopefully, you think of things that are equal or that look alike. So when we have symmetry, one side mirrors the other side. And so a figure has symmetry if it can be translated, rotated, or reflected onto itself. Now, that is why it goes into this section with transformations, because you technically can do transformations to create symmetry. However, we're not going to be doing any transformations in our homework. So think of it this way, right? Say you have an image drawn on a piece of paper. If you could fold that image in half and it matches up exactly line for line, like the left matches the right, then that figure has symmetry. The other way it can have symmetry is if you rotate it and it still looks like itself. Meaning that, let's say you rotate something 90 degrees, and even though the vertices have changed their locations, if the figure still looks like how it did before you rotated, that has symmetry as well. And now, I know I gave two different things. That's because there's two types of symmetry. The first type is line symmetry, and that goes with this definition here. And the second type is rotational symmetry, which is this type here. So let's first talk about line symmetry. Okay, so that's when a line is drawn through a figure that creates an exact reflection of one side on another. Okay, so imagine you had a triangle, and if you were to draw a perpendicular line right down the top of that triangle all the way to the bottom, and then you looked at both triangles now, the left and the right, if those are the exact same size and shape, that means that that triangle has line symmetry. On the other hand, rotational symmetry is if we actually rotate the figure. So if a figure is rotated X degrees and its image still appears as if it were never rotated. And I'm going to show you guys how that would look with a square here pretty soon. So line symmetry and rotational symmetry. So let's go ahead and look at these shapes here. Okay. So first thing I want you to note is that this triangle is what we call equilateral, meaning all three sides are the same. This is a rectangle, which means the top and the bottom are congruent, and the left and the right are congruent. The next shape is a square, so we know all four sides are congruent. And then the next one is just what we call a parallelogram, meaning the top and the bottom are congruent, the left and the right are congruent, but also opposite sides are parallel. So remember our markings for parallel. So when I look at that triangle on the left, it is an equilateral triangle. So that means if I were to draw a line straight down the middle like that, that triangle would be cut directly in half. So side 1 is the same size and shape as side 2. Again, if I were to fold it over that dotted line, that would be like these edges would match up exactly with these edges over here. However, there's more than one line of symmetry. I could also draw it going this direction. So I could fold it over that line as well. And you guessed it, I have another one here. So there are actually 3 lines of symmetry in this equilateral triangle. Okay. Now let's look at the rectangle. The rectangle has 2 lines of symmetry. One that goes vertically, so if I were to fold it directly in half down the middle that way, or one that goes horizontally. And a square is a combination of those 2. So we still have our vertical line of symmetry, our horizontal line of symmetry. Let's see if I can get this exact here. But then it also has ones like the triangle, where if I were to cut it in half this way, we've all folded like a starburst wrapper before. The starburst wrappers, I think, are usually perfect squares, where I can fold it diagonally that way, or I could fold it diagonally this way as well. Okay, I hope that line's kind of off. Let's see if I can get it a little bit better. And notice all of those lines should be intersecting at the exact same point, right in the middle. And then finally we come to our parallelogram, right? If I were to fold this figure right here, even though the left and the right are the exact same size, when I fold it, I'd get this overlap like this, right? Like this part of this would stick out. Okay, same thing if I did the other way. If I were to fold it to this side, we would get some type of, well, I would call it like overlap in regards to like it's not matching up exactly. And that's because of these pointed sides right here. So we don't have a vertical line of symmetry, and if I did it horizontally, I'm pretty much the same concept happens, right? Like none of this right here is still going to stick out over right here. Okay, so with that trapezoid, there is no symmetry as far as lines go. Okay, and that's the first part of your homework tonight. It's just finding the line symmetry within the figures. Let's go ahead and look at rotational symmetry. Now, rotational symmetry requires a little bit more thinking, but I think you guys got it. Okay, so let's start with the square. Okay. Now, most of the time, rotational symmetry is based off the center of rotation at the middle of the figure. So I want you to think of this square as having a vertical and horizontal axis, let's say. Let's say that's at 0, 0. All right. Now, if I rotate this square 45 degrees. Now, how do I know that that's 45 degrees? That goes back to our rules of rotation. If I go from B to our center of rotation out to where B ends up right here, this angle is 45 degrees. Okay, because notice it would be half of this right angle. So that is a 45 degree rotation. Okay. Which means my next one is how much? Again, remember, think of it as having a vertical and horizontal line. Remember, B started right here, but now it's over here. So how much do you think that angle measure is? That's 90 degrees. And I want you to notice between this figure and this figure, if I were to take the variable markings away, so those point markings A, B, C, and D, would you be able to tell the difference between the figures? The answer is no. So we call this mapping onto itself, or rotating onto itself. That means that figure 1, technically I guess that's figure 2 after a a second rotation. Excuse me, figure 3, 1, 2, 3. Figure 1 and figure 3, again, if I were to remove the A, B, C, and D, you wouldn't be able to tell a difference between them because they have rotational symmetry, right? So now as I keep rotating in 45-degree increments, right, this would then be 135. Notice that that does not resemble figure 1. But then if I go another 45 degrees, that gets me to that 180. Remember our, trying to draw some good looking lines here. Our B started right here through the point of rotation to where it's at, since 180. Notice again we have rotational symmetry again. Notice we're not all the way, in order to go all the way back, B has to end up right here. So let's go another 45. So that's going to be 225. Let's go again. And that brings us to our 270 degrees. Whoops, guys, sorry, I labeled that one incorrectly. A should be right here, B should be right here, C and D. Because if it was like that, if it was like the one I just had, that means it would be done 360, right? And then if we wanted to get to 360, we do another 45, and then finally one more to get to that 360 degrees where A would be matched up exactly where it was as long as B and C and D, okay? So just remember the center of symmetry, that's the point the figure is rotating around. Now here's a new term, the order of symmetry. So the order of symmetry is the number of times a figure maps onto itself between 0 and 360. So you have 1, 2, 3, and then by the time we get back to 360, that would be 4. Okay, so the order of symmetry for this figure is 4. And the magnitude is the smallest number of figures is rotated to map onto itself. The smallest angle a figure is rotated to map onto itself. And the way that you can find magnitude is 360 divided by the order. So notice, guys, that it took us, so this figure right here is the one that looked exactly like our very first image, okay? And that was a 90-degree rotation. So if we do 360 divided by, which our magnitude was 4, because again, it maps onto itself 4 times between 0 and 360, that gives us 90 degrees, which is what we just saw right here, okay? So magnitude equals 360 divided by order. Order is the number of times a figure maps onto itself between 0 and 360. So let's look at it from a hexagonal perspective. Okay, so remember we have our center of rotation here. You have your vertical axis, you have your horizontal axis, and notice that's a regular hexagon. So I'll also help you out with kind of knowing this, that when I draw this angle in right here, that is a 60-degree angle, okay? And the reason I know it's 360 is if, imagine I took this as a circle and I divided it up evenly like this. All those triangles are the same size. So I have 1, 2, 3, 4, 5, 6 little angles in there. 360 divided by 6 is 60. Okay? So I know that this angle right here, to get this point to that location, would be a 60-degree angle. Okay. Also, another way you could think of it is that there's 6 vertices. 1, 2, 3, 4, 5, 6. And anytime a figure is regular, its order will be its number of vertices that it has. So notice that the square had, its order was 4. So here, our order equals 6. So to find our magnitude, it's 360 divided by 6. That is 60 degrees. Okay? And then if I have a triangle that is what we call scalene, all 3 sides are different, this will not have rotational symmetry. So not rotational symmetric. Okay. So your homework is simply just, the first part is determining whether or not there's line symmetry in a figure. The second is determining whether or not there's rotational symmetry. And then you have to find the order and the magnitude. That's it.